Here's another problem on the analysis of a perfect frame, and we are going to use a method of joins in this problem. So we need to find one, the support reactions, and two, the forces in members. In order to find the support reactions, you need to know the distances at which the force 10 kilonewton and 12 kilonewton are acting. That is, if I draw extend the line of actions, you need to know the distances to say point F and point G from either A or B, and that distance is not directly given in this figure. You have got the supports separated at 5 meter, and you've got a right triangle here, the bigger one, it is 60 30 here, and therefore this is a right triangle. And you've got another right triangle here, EDB. We've got 60 here, 30 here, and it's again a right triangle. And also you can see this is an equilateral triangle because you have got 60 60, and therefore this is 60 degree. So side AC will be equal to CE, and that will be equal to AE, and the total distance is 5 meter. Let's see how we can find the distances to the forces 10 kilonewton and 12 kilonewton here. So what I'm going to do is just use the basic trigonometric functions to find the distances to these two forces. So as you can see in the figure, triangle ACB is a right triangle and AB is 5. Therefore AC will be equal to AB cos 60 or AB sin 30, and that will be equal to 5 sin 30 or 5 sin 60, that's equal to 2.5 meter. So your distance AC is 2.5, and therefore CE will be 2.5 and also AE will be 2.5. Here. So therefore EB also will be 2.5 because that is 5 minus AE, that will give you the distance EB. Now if you consider the triangle AC, say let's call this F and let's call this G. If you consider the triangle ACF here, AF will be 2.5 cos 60. So that is AC cos 60, 2.5 cos 60, that is 1.25 meter. So you have this distance 1.25 and therefore, excuse me, this also will be 1.25. And now if you consider the small triangle EDB here, and again considering this as a right triangle, because as I said this is a right triangle here, is 60 30 and this will be 90. So ED will be EB cos 60 or EB sin 30, that is EB sin 30 or EB cos 60, that is equal to 1.25. so this is going to be 1.25, and therefore EG will be ED cos 60, that is equal to 1.25 cos 60, 0.625, and therefore this is 0.625, and then you have distance AG equal to 1.25 plus 1.25 plus 0.625, that is equal to 3.125. So you have AG is equal to 3.125 meter. So that is the distance to the line of action of the force 12 kilonewton. And now we need to calculate the support reactions, and you have to use the equation of equilibrium, that is summation of moments equal to 0. Now taking the moment of the forces 10 kilonewton and 12 kilonewton, and also considering the reactions, you have 10 kilonewton acting at 1.25 in the negative y direction, creating a clockwise moment about A, so a negative moment. 12 kilonewton acting at 3.125 from A in the downward direction, therefore creating a clockwise moment and hence again negative value. And also you have RB acting at 5 meter from A in the upward direction, therefore creating a counterclockwise moment and a positive moment. So for the moment equation, you have Ra into 0 because that's passing through the point A, and 10 kilonewton into 1.25. So Ra into 0 minus 10 into 1.25 minus 12 into 3.125 plus Rb is equal to 0. That will be your moment equation. So that's shown here. You have your moment equation, that is Ra into 0 minus 10 into 1.25, that is the 10 into 1.25 minus 12 into 3.125 plus Rb into 5 equal to 0, or Rb is equal to 10 kilonewton. So you've got your Rb, that is equal to 10 kilonewton. And now applying the vertical equilibrium condition, you have two vertical forces acting downwards and two vertical reactions acting upward. So Ra plus Rb is equal to 10 plus 12, that is equal to 22 kilonewton, and therefore you have Ra equal to 12, which is 22 minus 10, that is 12 kilonewton. So you have Ra equal to 12 and Rb equal to 10. So that's your reactions. Now you can move on to individual joints. So if you consider the joint A here, you have a reaction A, 12 kilonewton, and two forces on member 1 and member 2. And if you consider joint B, you have 10 kilonewton and two forces on these two members. So let's consider the joints individually. So that's shown here. You have your joint A with Ra, that's 12 kilonewton, and joint B with Rb 10 kilonewton. So for the vertical equilibrium and horizontal equilibrium of this joint, we can use the equilibrium conditions. You have the components of force. Let's call this member 1 and call this force 1, and let's call this member 2 and force 2. So you have your horizontal component and vertical component for the force 1. So for the vertical equilibrium, this force should be equal and opposite to the vertical component of force F1. So the direction is downwards for vertical component, and therefore this will be in the negative x direction, and therefore you have F1 acting towards the joint, and therefore it's a compressive force. And because this is acting towards the negative x direction, for horizontal equilibrium you should have F2 acting in the positive x direction. So the equilibrium equations will be Ra equal to, you have this angle 60 because this is 60, and your sides are, this is F1 cos 60, F1 sin 60. So Ra equal to F1 sin 60 and F2 equal to F1 cos 60. So from these two equations, Ra equal to F1 sin 60, you can calculate F1 as 13.856 and F2 equal to F1 cos 60, you have F2 equal to 6.928. This is calculated divided by Ra divided by sin 60. And you are applying the same conditions here. You have force F3 and F4, and you have the components for the inclined force F3 like this, and for vertical equilibrium you should have this force in the downward direction, and therefore this will be towards positive x direction, and therefore the force F3 will be towards the joint and hence a compressive force. And because this is 30 degree, this will be again 30 degree, and you have F3 cos 30 and F3 sin 30. So for the equilibrium you have F3 sin 30 equal to Rb and F4 equal to F3 cos 30, and F4 should be acting in the negative x direction for the equilibrium. So you have Rb equal to F3 sin 30, or F3 equal to Rb divided by sin 30, that is 20, and F4 equal to F3 cos 30 here, that will be 17.32, and F3 is 20 kilonewton. F4 is acting away from the joint, and also F2 is acting away from the joint. So now we are moving on to the next joint here, which is joint E here, and you have forces F2, this is F2, and you have F4 here. Both are acting away from the joint, and you need to find the forces on this member here and the member here. So that's what we are going to do next. We have F2 and F4 already known as 6.928 and 17.32, both away from the joint. So F2 6.928 and F4 17.32, both acting away from the joint, and you have to find F5 and F6. So with a simple observation, you can see you have two forces here. So F5 will have a horizontal and a vertical component like this, and so is the case with F6. You will have a horizontal and a vertical component. So for the vertical equilibrium of this joint, you should have F5 and F6 acting in opposite directions. Then only it will be equilibrium. So for the vertical equilibrium, you have F5 sine 60 plus F6 sine 60 equal to 0, or you can say F5 equal to minus F6. Let's call this condition 1. So, and then let's assume a direction for the forces. It is to be noted here that because we don't know the direction of either F5 or F6, we are going to assume a direction, and if you calculate a positive value to the force, that means your assumed direction is correct, and if you calculate a negative value to the force, then your assumption is wrong. Then you need to reverse the direction. Now I'm going to assume two directions for these forces. Let's assume F6 acting towards the joint and F5 acting towards the joint. So we already have one condition, F5 equal to minus F6, and we don't know the direction of either of the force. Just assume a direction, and if you have these directions, then you should have a force in this way and this way, and also for F6 you should have this direction and this direction. So now for the horizontal equilibrium, the force F4 17.32 is acting towards the positive x direction, and so is the case of F5 horizontal component. This is 60 degree and this is 60 degree, so you have F5 cos 60 and F6 cos 60. So F5 cos 60 is acting in the same direction of F4, and F6 cos 60 is acting in the same direction of F2. So for the equilibrium, you have F4 plus F5 cos 60 minus F6 cos 60 minus 6.92 is equal to 0. These two are taken negative because they are acting in the negative x direction. So you have F4 plus F5 cos 60 minus F6 cos 60 minus F2 is equal to 0. And from that solution, you have F6 equal to 10.392 kilonewton. Because F5 equal to minus F6, we can apply that condition here. So you have F4 minus F2 minus F6 cos 60 minus F6 cos 60 equal to 0, or F4 minus 2 into F6 cos 60 minus F2 equal to 0. Solving this, you get F6 equal to 10.392 and F5 equal to minus F6. So F5 is minus 10.392, and because F5 have got a negative sign, you have to reverse the direction of F5. So the direction of F5 will be away from the joint. So you can change the direction of F5 here, because that should be away from the joint. and what you need to do is change that to away from the joint. So your all the directions will be reversed, and that will be the direction of the force. This is rho, and again this is rho. So this will be the correct force direction. I'll repeat again. If you don't know the directions, assume a direction for the forces and calculate the force, and if you are getting a negative value, then your assumed direction is wrong. So that's what we got here. F5 is a minus value, and therefore you should reverse the direction of force on the member 5. So now that we got F5, F6 and F2 and F4 are already calculated here. So now we can move on to the next joint, which is the joint D here, and we already calculated the force on F4 and F6. This is F6 and F4, and we also know this force here. What we need to do is to calculate the force on the member here. So let's move on to that joint, the joint D here. What you have is your force on 3, force on 6, and you need to calculate the force on the member 7. And what I have shown is horizontal lines parallel to the x-axis. You know this angle is 60, and this is 30. Therefore this is 30, and therefore this is 30. So you know the force on 6, 3, and you also know the 12 kilonewton force here. Force F3 is, let's see what the force on F3, that is 20 kilonewton, and force F6 is here 10.392. So F3 20 kilonewton, and F6 10.392, and this is 12. You can either apply the horizontal equilibrium or a vertical equilibrium. So for the vertical equilibrium, what we have is let's consider the horizontal equilibrium, because that's the equation I have written here. So you have, for the horizontal equilibrium, let's draw with a different color here. You have components of force F6, vertical and horizontal, components of force F3, vertical and horizontal, because these are in these directions. You have this one upward and this one in negative x direction, and components of force F7, you don't know the direction yet. So what you have is, you don't have to consider this one because that's a vertical force only. You have F6 cos 60, yes, this is 60 and this is 60. So this is going to be F6 cos 60, and this is going to be F3 cos 30. These are in opposite directions. So F6 cos 60 plus F3 cos 30, minus F3 cos 30 plus F7 cos 30. Let's call this, assume the direction in this way. That will give you the horizontal component in this direction. Again, if you are getting a negative value after calculation, you are wrong. So that will give you F6 cos 60 plus F7 cos 30 minus F3 cos 30 equal to 0. And F6 is 10.392. So 10.392 cos 60 plus F7 cos 30 minus F3 is 20. 20 cos 30 equal to 0. And from that, F7 equal to 14. Suppose we have taken F7 in this direction here. If you have assumed this direction, then your equation will be F6 cos 60, that is in the positive direction x, minus F3 cos 30, and if you assume the direction of F7 away from the joint, then this will be in the negative x direction, so you will get minus F7 cos 30 equal to 0. If you solve this equation, you will get this is F7. If you solve this equation, you will get F7 is equal to minus F7 equal to 14, or F7 equal to minus 40. And therefore, your assumption of the direction of force is wrong, and you need to change it to this direction or towards the joint. Go through this problem a couple of times, and if you have any doubts, just comment on the video and I'll get back to you.